Okie doke. So I think I'm all set here. Mostly all set. I just remembered. Got that. Just in case Nick needs to yell or something, it'd be good to be able to hear him. Okay. So, yeah, I've been trying to get some things graded for classes, including this class. That's been going a bit slowly, and so I noticed that I didn't get much put up there as far as like videos for chain rule, that kind of thing. It says homework for the chain rule is due tonight. Yeah, well, you know, if you're late on that because we haven't really talked about it, that's okay. I mean, you know, we are all dealing with you know, this different sort of scheduling and all that, and so you know, we're all going to have issues at times, and definitely I will, I'm sure. So I have so far. So with that, yeah, we want to talk about probably a little bit more on the product rule and quotient rule real quickly, and then chain rule, because that's what tends to cause people the biggest problems. The quotient rule can cause problems, but you know, when all is said and done, the quotient rule I think is mostly a matter of practice. You know, you'll do fine with that if you practice it enough. Because it really, you know, it's just kind of sticking things in, and quotients are pretty darned easy to see, okay? But again, as we talked about very early on in the class, the chain rule, where you're looking at composition of functions, that is just something that for whatever reason our education system does not really push. There's this huge push to get everybody into calculus, yet they don't really talk much about composition of functions, and that's a big deal in calculus. And I've never really understood that, but amazingly, no one seems to listen to me on trying to do more with it. So. So it continues to be a bit of a problem for people. So questions on anything right now? Looks like a no. Okay. So again, in 2.3 we had the product rule. And we did see that last Thursday. We mentioned the product rule. And so in that case, if I have a function f of x equal, h of x equal f of x times g of x, so if I have something that looks like that, then I can take its derivative by taking the derivative of the first, multiply it by the second function, add to that the first function times the derivative of the second function. Now, when I write this down, I'll often write it many different ways. Sometimes I might do the g prime first here, and then the f of x, and so forth. The thing you want to remember is, one, addition, it's commutative. It doesn't matter which order I put those two things in. It still works. And then multiplication, commutative. It doesn't matter which order I put those two things in, it still works. 3 times 2 is 2 times 3, that kind of thing. And so what I remember is I need to take the derivative of that thing, which seems reasonable because I'm taking derivatives. I need to take the derivative of that thing. Seems reasonable. I'm taking derivatives. But they don't go together. Okay, the two derivatives don't go together, and so they're separated by a plus. That I can remember. And then an example that kind of just shows us by some other method that this does seem to work is, suppose I take h of x, and I just take something very simple like x minus 1 times x plus 1. And so now, according to this rule, h prime of x is, well, I'll take the derivative of this thing, so the derivative of x minus 1 with respect to x times x plus 1 plus the derivative of x plus 1 with respect to x times x minus 1. So there, see, I screwed it up already, right? And I didn't really start that on purpose this way. I mean, that's what I did this time. Here I'm showing the derivative first in each of those products. That's okay. It doesn't matter. Right? I have to take the derivative of that function. I have to take the derivative of that function. I do them both. They don't go together. And so I have those. And as far as writing this step out, if you can do if you say, I don't want to write that all the time. If you do them correctly, if you get the right answer, I don't need to see that step. I can tell here that you're using the product rule if I see like a 1, or even if I can multiply by 1, I don't even need to do that. Yeah, if you're getting it right, more power to you. Great. If you're not, do every single step until you get them right all the time, and then you start leaving them out and so forth. So, it's just what do you need to do to get it right. So here I have x plus 1 plus x minus 1. Well, I got a 1 minus 1, that's 0, and an x plus x, I get 2x. Now, the reason I do this example is that this h of x, which is x minus 1 times x plus 1, well, if I just multiply that thing out, it's the difference of squares idea here, right? So I get x squared minus 1 when I multiply that out. Now, let's take that thing's derivative, h prime of x. Well, that's the derivative of x squared with respect to x minus the derivative of 1 with respect to x. Derivative of x squared, power rule, right? Bring down the 2, subtract 1 from the 2 like that. There's my power rule. And then constant rule, I just get 0. And so once again, I get 2x. And so we see that, yeah, it seemed to work either way I did it. Didn't seem to matter. Well, that's a good thing. That's the way math is supposed to work. And so we get 2x either way. Okay, questions on product rule right now? Anything? Nothing? Okay. Well, so let's look at the quotient rule. And like I say, the quotient rule, as far as seeing a quotient, oh, that's easy. I mean, we get the line across there and so forth. And so if we have this quotient rule, that says if I have some h of x that's, I decide looks like one function divided by another function, then I can take this more complicated derivative. Now here, yep, order matters. Matters a lot. Okay, well, a lot. You get you get negatives. You get the negative of what you should get if you do it backward. But it ends up looking a lot like the product rule, which in a lot of ways seems like it ought to. So it looks a lot like the product rule, I think, anyway. But again, it matters a lot that we have to take the derivative of the top first. And, you know, again, in a lot of ways, as far as remembering, I don't know, it's the top. Start at the top, you go down. I mean, that's often how we, you know, that's how I read lists. That's how I do everything. You know, I start at the top and I go down. And so in that way, it seems reasonable as far as just a memory sort of thing that, oh yeah, I ought to be able to remember, take the derivative of the top, multiply by the bottom. See, so it's looking a lot like the product rule. Then minus they still sell Wheaties? I don't eat Wheaties. Actually, I eat Cheerios. I was thinking, you know Wheaties? Breakfast of Champions? I'm eating too many Wheaties. Keep breaking the chalk. So here we, so it's a lot like the product rule, except see there's this minus. And so that's why it matters that, now here, if I say f of x and then g prime of x. So again, I've had to take the derivative of the top. I've had to take the derivative of the bottom. They don't mix. They're separate, and so I multiply by the other thing. But it matters a lot that I take the derivative of the top first because of that minus. And then divided by g of x. Oops, squared. And that's kind of weird too, that g of x squared getting thrown in there. But it works, and again, I could take some class time to go through the limit stuff and all that. I just kind of figure if you're like a bio major or something like that, you don't care most likely. You just want to know what the darn rule is and how to get an A on the test, right? That's if you're a math person, you've got plenty of time to work on such things, and if you have those interests and all that, you can always ask me more. But I will. I have some videos on the product and quotient rule. I just haven't had a chance to upload them yet. But I haven't done the proofs yet of those, and I'll probably do videos of that as well. So, okay, so there's the quotient rule. And again, we can take something that we could do a different way just to see that, hey, it works. And, that might be something like h of x equals 1 over x squared. That's a quotient. And so if I want the derivative of that, again, I just plug everything in. So I need the derivative of 1 with respect to x, and then times x squared, and then minus 1 times the derivative of x squared with respect to x, all divided by x squared squared. So I do that, and derivative of 1 again is, that's a derivative of a constant, so I just get 0. So this is equal to 0 times x squared minus 1, and power rule, x squared, I get 2x when I do that. Take that derivative. And then divided by, well, x squared squared is x to the fourth. And so I have that, which is just minus 2x over x to the fourth. But I can simplify that a little bit. I got x over x to the fourth. I can just write that as minus 2 over x cubed. Well, h of x, another way to write that is x to the negative 2. And so if I want that derivative, well, that's a power rule. So bring down the negative 2, x to the negative 2 minus 1. So that's negative 2x to the negative 3, but that can be rewritten as negative 2 over x cubed. Same darn answer. I love this math stuff, at least when it works out. When I screw something up, then, you know. Okay, so questions on that? So, you know, it's one of these things that if you're given just, you know, these two functions, one divided by another or one multiplied by another, I don't see any reason why you can't get this far, right? I mean, it's just a rule, you plug things in, right? And there is no calculation done getting this far. I literally, right, just took the 1 and put it in that blank spot, took the x squared, put it in that blank spot, the 1 again, the x squared, you know, so I just stuck them in to those pieces, haven't calculated a darn thing. You know, so I should be able to get that far. Now, as long as you've got simple functions, yeah, this stuff, you know, I should be able to take a derivative of a constant. I should be able to do the power rule, that kind of thing. You know, I get questions about how much simplification do you need to do. Well, you know, a lot of that just depends on where you're going. If all you had to do was take a derivative and just take it, you know, you just wanted to know what it was, well, I guess that's reasonable. That's kind of unreasonable. I mean, because you can multiply by 0. You can multiply by 1. So, like, up here, that's kind of unreasonable to leave it like that, but that's pretty reasonable. But on the other hand, if I had to take a second derivative, well, I'd rather simplify to that, because that I can rewrite as a power rule and just do the power rule in that case. Whereas this, I'm kind of stuck doing the quotient rule. You know, so what you simplify to really can depend on what it is you're trying to do. If I just have to stick numbers in, right? If I was asked, what's h prime of 2? Oh, well, actually, in that case, I might put 2's in here. And then simplify that using a calculator or by hand or whatever I did. Because once I put the numbers in, I don't know, it's all just a bunch of arithmetic at that point. So you know, I often get that question, you know, how should I simplify, that sort of thing. Well, in reality, it's what do you need to do? You know, what's reasonable for what you're trying to do? I was, you know, it was very weird, my year at the Air Force Academy, because my first semester I taught a bunch of Calculus 1 sections, and they took these quizzes, and on those quizzes, they had to get the syntax of the mathematical language correct. Okay, so, for instance, if they didn't simplify, that was wrong. You know, that kind of thing. Well, it was kind of weird because the biggest thing that just caught my eye about the whole thing was that, you know, suppose you had an answer that was supposed to be 2x, and you wrote it as x times 2. That was on the quizzes, not on the exams, but on the quizzes, that was wrong. Okay? And, you know, and it was one of those things that I was never quite sure of, what the right answer ought to be for something like that. Because on the one hand, that is correct, right? You know, I mean, that's still whatever x is times 2. And that's what that is, you know, whatever x is times 2. They're both the same. But on the other hand, never have you opened a math book and seen x2 like that for 2 times x, right? You've never seen that in a math book. Yeah. And so it was really kind of weird because I thought, well, yeah, on the one hand, not a big deal, but on the other hand, it's like, well, if you've never seen it that way, why should you think that's the right way to write it? You know, I mean, it's kind of a, you know, and if you think of math as a language, right? Well, every language has its rules, and so, you know, if we're speaking English, we might talk about, well, we'll go with purple. How about that? Because it's red and blue. I just want to use one color, so we'll say purple. Mix red and blue. Right? You talk about in English a purple shirt, but in Spanish you would talk about a shirt purple, I believe. Correct? Yes. Right? So, you know, 2x versus x2 depends on the language. And so, you know, there are some things that, you know, they aren't really wrong, but it's like fingernails on a chalkboard to somebody who looks at that language a lot. Okay, it hurts my soul, right, to see some of that. So, you know, just kind of think about the language. Math is a language, and writing with good grammar, that kind of thing. Okay, so any questions on product rule, quotient rule right now? Okay, well, 2.4, chain rule. This is a tough one. I really believe it is because we do not stress composition as a binary operation like addition or multiplication or subtraction or division in our progression of mathematics. You know, at some point you learn about it, maybe Algebra 1, Algebra 2, somewhere in there. You know, but it's really not treated in depth. You don't do a lot with it, and like I say, I think that is kind of what causes a lot of the trouble with the chain rule. Because on the one hand, you know, if I just ask you, okay, what's the derivative of x squared with respect to x? You all would say 2x. Right? Big deal. Piece of cake. And if I said, hey, what's the derivative of sine of x dx? You might panic for a moment trying to remember, okay, plus or minus. But you would come up with cosine of x, right? So, and much the same way with like the product rule or the quotient rule, right? If I'm just giving you two basic functions to take a derivative of, not a big deal. I mean, I learn the power rule, I learn sines, cosines. Once I know those, I mean, it's always the same thing. Now the problem is that what happens here is we're looking at h of x is equal to a composition of functions And the way, there are a couple different ways we talk about the chain rule. One is with the prime notation. We'd say h prime of x is f prime of g of x, and then times g prime of x. Okay, so that's, I mean, I like that notation. That's a nice way to go. And then the other, the fractional notation or the Leibniz notation, you would say something like dh dx. And I also like this notation because it looks like it ought to be true, and that is df dg dg dx, like that. And if you think of multiplying fractions, right, I would get to cancel out that numerator, that denominator, and I would get d, oops. What do I want to, well, actually that is what I want to write. Yeah. So, yeah. Didn't look as nice as I thought, but it does, you know, those cancel out. Usually I guess it's done with dy's and stuff, but so we're just taking the derivative of two things, and that part's simple, but it's this part here that just tends to really mess people up a lot. Now, I've always liked the sort of the idea that what I tell people, you know, when you want somebody to leave something alone. So the first time I ever heard this, I was working on my car, and I said something to my boss at work about, you know, do you think I should mess with the carburetor? And he looks at me and he says, hey, you know, carburetor is French for leave it alone. Okay? Now, the next time I used it, it was when we had our second girl, and our older one kept messing with her, would wake her up all the time and all that kind of stuff. And so we said to the older one, oh, you know, Laura is French for leave her alone. She understood. She still didn't leave her alone, but she understood. And here, inside, so we talk about with composition sort of an outside and an inside function. Inside, in this case, is French for leave it alone. Don't mess with it while it's on the inside. And so, you know, if I have something like h of x is equal to the sine of x squared, what I need to do is look at that and realize I have these two functions. I have the sine of x and I have the x squared function. Okay? I have an outside and I have an inside function that way. All right? And so this is outside and inside. And once I realize that, then all I have to do is take their derivatives. Okay, so h prime of x and multiply those two things together. But here's where you have to be careful. Is and this is one of those things that maybe just practicing various ways, you know, whatever ends up working for you, but you could come here and say, oh, what's the derivative? You know, I see these two functions, take their derivatives, cosine, don't fill anything in yet, right? And then derivative here is 2 times whatever that was. right? Is you sort of think of these as sine of something and something squared, and think about those derivatives that way. Is, oh, derivative of sine of something is cosine of something. Derivative of something squared is just 2 times that something. Now, if it's the inside function, right, that's what went here. And, you know, I mean, I just do my x like that, and my x squared there, you know. And I could stand up here and just say, oh, well, you know, look at the outside function, take its derivative, leave the inside alone, and, you know, I can say that, and I can say it over and over and over and over. And some of you will still screw it up. Okay? I can say it different ways, and some of you will still screw it up. It's a practice thing. You have to take it slowly. You know, if you're getting the wrong answer, if hey, you take to this, as they say, like fish to water, and you just go, oh yeah, piece of cake, I can do this all day. Great, awesome. You know, do it all day. That's a really good idea, actually. But you have to, you know, but if you have trouble with it, you need to find a way to write things down. But what I'm trying to get across is it's not that much at any given point. It's always just these 2 functions that I'm dealing with. And I've got the outside one, I've got the inside one. I need both of their derivatives, but the inside one goes back inside the outside function when I'm done. Okay, so I need to be able to do that. But that's all there is to a chain rule, is that idea. Now, where does all hell break loose, right? And things get really nasty. Well, this is not something that I, want you all to spend lots and lots and lots of time on, partly because with technology, some of it is a little silly to spend a ton of time on. But on the other hand, somebody's got to check that the technology is working, right? When you hand something off to technology, you need to have some idea that it is doing what you want. And so being able to do some checks on it with simpler things is a really good idea. But, so suppose I'm given, something like x sine x to the 4th. Right? And I want that derivative. See, this is where it just starts getting complicated, but you want to take things just one step at a time. And so you have to look at it and you say, what's the big picture of what's going on? And in this case, the big picture is that I have a composition. I have an inside function and an outside function. That's sort of the last thing that happened. That's the big picture. If you stand way far away from this, you probably can't read the x sine x, but you can see that, oh, there's something to the 4th power. So I start with a chain rule. And so starting with that chain rule says, well, I need to take the derivative of something to the 4th with respect to x. And then I need to take the derivative of whatever that something was with respect to x. Now this part in a way, is sort of simple, because I just write that in, and that statement just makes total sense. Well, at least as much as a product rule makes sense, right? I can look at that and go, oh, I know what I need to do. Derivative of x times sine of x plus, and so forth. But here, the problem is, there's not a really nice way to put the x sine x in here and get the idea across that all I want to look at is that 4. And there's our problem. I mean, there's a bit of a problem with notation. Because, I would like to have this just say, hey, all you need to do is deal with the derivative of something to the 4th. And the best I can do is leave it blank for the moment and just look at, I've got something to the 4th power, I want to take its derivative. And so, if I do that, then taking that derivative, I'll get 4 times that something to the 3rd. Now I can fill in that something because my derivative stuff's gone. And I'll put in the x sine x. And again, is that the correct mathematical? No, there is no correct way. That's the problem. I mean, it's just, we don't, for whatever reason, we haven't really developed a great notation for this. And so, we do something to try to get that idea across, just mess with the outside function first. Now, with me, I've done this enough and so forth that I would just, I probably wouldn't write that down. I would just go to that. And that does it for me. That takes care of it. But you need to think about that that's what you're doing. It's, when you first start this out. And so, again, it's kind of what works for you, and try different things to get this idea. And then we have a product rule. So I'm just going to, I'm going to make a nice big space for it and then do that product rule. I have the derivative of x with respect to x, sine of x, plus x times the derivative of sine of x with respect to x. But you want to put a lot of parentheses in there. And so we get 4 x sine x cubed, and then here we get sine of x plus x and cosine of x. And unless I need to do more, I'm done. I'm not doing any more with it. I can, right? I can multiply. I've got a sine cubed x. I've got an x cubed there. I can multiply things through. I could get a sine to the 4th. I could get an x to the 4th there, with the sine cubed and cosine and so forth, But I see no reason to keep going. That's good for me. Unless I decide I have to do something else, and then maybe it might be worthwhile changing things. Okay, but hey, I'm done. Okay, but this is the chain rule can get really, really nasty. By the time you have products and quotients and things like that, right, it gets very, very nasty. Now, but here's something as far as if you think of a quotient rule, right, h of x is f of x over g of x. So if I have that, but notice that's f of x times g of x to the negative 1. Now it's a product, and I can just do the product rule along with when I have to take this derivative, I need a chain rule. So if I want h prime of x, it's the derivative of f of x with respect to x times g of x to the negative 1, and then plus f of x times the derivative of g of x to the negative 1 with respect to x. Well, that's as simple as I can make it. That's just f prime, whatever it turns out to be. That's still 1 over g of x, or g of x to the negative 1, however I want to write it, f of x. But now this, I can do something with this derivative, because I can first do the power rule, right? Bring the negative 1 down, subtract 1. And so this is derivative of f with respect to x times g of x to the negative 1 plus f of x. Now, when I take this derivative, all right, I'm going to get a minus 1 times g of x to the negative 2, okay, because I subtract 1 from the 1. And then, because of the chain rule, so I did that outside part. Now, because of the chain rule, I need my g prime of x. Now, here's the thing, is notice if we start kind of looking at pieces, so here's that f prime. Here's f without a derivative. There's the negative, right? Remember on the quotient rule, I had minus f times the derivative of g. Oh, there's f. There's the minus. So minus f times the derivative of g, g prime. And, oh, but I'm dividing by g of x squared. Oh yeah, we divide by g of x squared. Here, I'm just dividing by g of x. Oh, but if I want to divide by g of x squared, I just make it g of x over g of x squared instead of just 1 over g of x. So I've just made, actually, the quotient rule. Doesn't look much like it in this form, but if I mess around, you know, move things around, put things in the bottom, in the denominators and so forth, I've got the quotient rule right there. So I can make the quotient rule from the product rule and the chain rule. And it actually can come in handy to think about it that way. If you have a quotient, is instead of trying to do the quotient rule, sometimes it just, this, as nasty as it looks right here, might actually look better in the end when you put everything together, the actual functions. So, you know, that would be something like if I have h of x is equal to, and you know, we just take something like x squared plus 1 over, you know, x minus 3, something like that. Then, you know, if I wish, I can think of that as x plus 1 times x minus 3 to the negative 1. So that's this idea, right? Is I just, instead of doing a quotient, do a product, but I'll need the chain rule because of that negative exponent. And so if I want h prime of x, again, derivative of the first, so that's derivative of x squared plus 1 with respect to x, but then just multiply by x minus 3 to the negative 1, and then plus x squared plus 1 And now I need the derivative of x minus 3 to the negative 1 with respect to x. So I have that. And that first part is nice. It's just the derivative of x squared plus 1 is just 2x. So I get 2x times x minus 3 to the negative 1. And then plus x squared plus 1. And now, multiply, and again, I like to just put some big square brackets and say, well, okay, all this thing I'm going to do is going to go in there. So I need a derivative of this. And, well, it's a power rule, right? I've just got something in the negative 1, so just bring down the negative 1 and leave what's on the inside alone, subtract 1 from the negative 1, get the negative 2, and now times the derivative of x minus 3 with respect to x. And, well, that's just 1. And so I end up with 2x times x minus 3 to the negative 1 plus x squared plus 1. Well, I've got that minus, so I'll bring that minus 1 out, make that minus, and then x minus 3 to the negative 2. And the derivative, again, of x minus 3 is just 1, because derivative of x is 1, derivative of negative 3 is 0. And so I get that. It's not pretty, but it's there. It's the derivative. Okay, so I could have used the quotient rule, or I could turn it this way into a chain rule. And so the chain rule just ends up being very handy, in particular for powers, I think. So right before, if you had like f of x equals x plus 2 to the 10th, right? How would you have to do that derivative? Right? You'd have to multiply this thing out. Right? You'd have x plus 2 times x plus 2 times x plus 2, dot, 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 to x plus 2. And so when we first started, we just had sums and power rules, that kind of thing. So I'd have to multiply all of that together to get x to the 10th plus, whatever. Yuck. Well, then we did section 2.3, and I've got the products rule. Oh, well, I can do this with the products rule. Just kind of take each piece as it goes, and there's a derivative of that, and then times that thing, plus that thing times the derivative of that. But how do I do the derivative of that? Well, I just keep going in more and more. But that doesn't sound like fun. All right, so now, though, if I want f prime of x, well, I just look at the outside function as power rule, bring down the 10, x plus 2 to the 9th, and then times the derivative of x plus 2, but that's 1. And so just like that, I get 10 times x plus 2 to the 9th. So the chain rule, very handy for some things like that. Square roots, if I need to take the square root of something. But again, a square root's just a power, it's the 1/2 power. So it's that same idea. Questions on the chain rule or anything else at this point? No. Okie doke. Well, I'll work on my parts, the video and so forth in your project. We haven't gotten your project, but if we have to have that due, like next week sometime, that's, you'll probably actually like that better.
So anyway, I'll keep working on my stuff, you keep working on your stuff, keep questions coming, and I will see you on Thursday.